All right, team, let's revise. So, chapter 9 and chapter 10. Chapter 9 is probability. What I want to get through today is 9F and 9G. Okay? Now, before we can get there, 9A to 9E revises a couple of skills that you're meant to have known from year 10. I was informed that you guys are masters of this since year 10, so I'm just doing recapping now. Here we go. These are the things you need to know. How to use a tree diagram. That's the first thing. Number 2, you should know your Venn diagrams and how that links to Carnot maps. Hands up if you know what a Carnot map is. There's another name for it as well, just in case you're not sure. It's a two-way table. That's the name that I learned it as. So Carnot maps or two-way table. The next skill that you need to know after those are the concepts. So rules, essentially. You have the addition rule. You have the multiplication rule. And the last one, I normally don't like to mention it because it's meant to be logical, but it's the total probability sum, which we know that. Maximum probability, what is the maximum? 1. 100%. Okay, so I normally don't like mentioning it because it confuses you, but we logically know maximum is 100% or 1. Okay? So, let's go through some of the skills. I know that tree diagrams you should have, so that's 9A. You'll be doing a bit with tree diagrams, flip a coin, spinner, find the probability. Venn diagrams. This one I do want to check that you know, because that will link into Ex9F conditional probability. So, if you are struggling with this, this is exercise 9E. Okay, so I'm just trying to help you so that you know which one to revise. That's what I'm going to do over here to see how much of the probability section you know from 9E. Addition rule and multiplication rule. Let's see. Anyone know what the addition rule is again? What's the addition rule? Anyone know?
This is in the context of probability, right?
Yep, context of probability. I'll start off the first part of it. A union B is equal to?
PR A plus PR B minus PR A and B.
Very good. For those who don't know, please copy this one down. There are 3 things that you need by the end of next year. There are 3 rules in total. It's this one, there's the multiplication rule, and then the one that I'm going to teach you today, which is 9F conditional probability. Those 3 are the key ones that you're going to be using for probability questions. So that exam that Dylan's got, it's likely using one of these 3 rules to answer, or one of these concepts here. Okay? So that's your addition rule. If you don't know it, please copy it down. A union B is equivalent to probability of A plus probability of B minus the intersection between the 2. Technically, you don't need to memorize that. Logically, it makes sense. If you draw a Venn diagram. See, A union B just means color this. Whatever's A, color whatever's B. That's A union B there, right? That's unioning A and B. But what you can see is if I color A, so this is A, so that's what they're saying, probability of A. Now, if I add on probability of B, you can see if I add B, and I'm going to shade B right now. Whoops, I should do it in this color. I'll shade B. There's a section that I've overlapped. Okay, so I've counted twice. So I've just colored A, but by coloring B, I've also colored the intersection twice. Okay, that's why they say remove the intersection. A intersection B, that's why they say minus A intersection B. So if you colored A, you only need this extra section, but since you're adding on B, you're now doubling up in the middle. That's why you subtract the middle. Okay, so that's addition rule. Next one, multiplication rule. What is the multiplication rule? Does anyone know?
PR A given that B as a third times PR B is equal to PR A and B.
Very good. Now, this multiplication rule comes from your tree diagram, which you would have done intuitively when you learned tree diagrams. Probability of A times probability of B given A is equal to probability of A intersection B. This one is key for when I teach you 9G to do with independent events. Okay, so these are the two main rules that I want you to have sort of in your mind at the moment. So as I go into conditional probability, I am going to expect that you know how to do tree diagrams. You understand how to move from one branch to the next, which is multiplication rule. You understand Venn diagrams mapping into cardinal maps, okay, or two-way table. With that as your sort of prerequisites, then when I teach you 9F, it should make more sense, okay? Now, for those who aren't really strong with Venn diagrams and cardinal maps or two-way tables, I'm just going to draw a diagram here and just try to remind you how they link to each other. So if you don't know, please copy the diagram down. Here we go. This is A, this is B. Cardinal maps, we use a two-way table to illustrate the same idea. I'm going to do it in purple. A dash, B dash. Out of curiosity, what's dash mean again? Not. Complement. Okay, so it means that if I said A was the numbers rolling a dice, it's getting the even numbers, then A dash means not getting even numbers, which means you get odds. Okay, all of that, if you're confused with the notation, I'm saying that's 9A. Okay, so you'll be going back to 9A. So I'm zooming through 9A to 9E. Okay, that's all the skills that you should know from 9A to 9E. Here we go. How do you convert Venn diagrams into a cardinal maps? Are the four regions that you see here. So in the Venn diagrams, can you see that you've got just A only? So here I'm going to color just A. Anyone remember the notation? How do I describe that region? So just A but not B. Well, yeah, that's true. I literally just described it, didn't I? A intersection B dash. Okay, so this now represents here A intersection B dash is in yellow. This is your yellow region. If I color the next region, say green. A and B, very good. So this is A and B. So you can see here, if you total the probability, green plus yellow gives you the total probability for A. So all of A. Okay, so this is a two-way table. If you add vertically down, green and yellow gives you all of A. Similarly, if I color now the other region, just B only, we can see that blue and green, let me just label that. This is now A, not A, but intersection B. So B only, but not A. And that corresponds to this region. So you can see green horizontally, green plus blue should give you all of B. Okay? This would be all of not A, all of not B. Now, if you add all of A and all of not A, what should you get here? Everything. And how do you say everything in terms of probability? 1. This is what I was talking about before. Okay, if you add everything together, you 100% got everything. So, it has to be 1. So this is to do with probabilities.
Wait, to select every single element, right? Is an O? When you say there's no elements, you do O and then the slash.
Yep, that means null.
And which one's like all of it?
All the elements? You mean this one?
Oh, is that it?
That's the universal set. Epsilon.
So just back that up.
I want you to check that one out and make it up too. I'm trying to say, I know it goes loop, and then I come back down like that. That's how I normally draw it. As just know, when I do it, that's how I do it for universal set. And then when I do element, I just do that. So that's like X element of, I don't know, 3 to 1. And then this one is just what I've learned from textbooks when I was young. That's how I do it.
It looks like the dot you drew at the start of the year.
The dot?
The dot. With the little tie.
What dot?
The one you did with like one little motion thing.
The integral G.
Yeah. And it had a tie, like a little bow tie.
Oh, my signature. Whoa. That thing is like...
Who's gonna die?
Bro, this room is not safe. This room is not safe.
We're gonna die.
Bro, this is what
We're all
happens.
gonna die.
This is what happens when you get public school funding.
Well, that was quite scary, actually.
Can we just like leave that open? See if one of us gets hit on the head. Go home.
I'm trying to get one off. Make sure that door's
Now have to go to uni. Just...
All right. Shh. I'm trying to teach. We're wasting more time. Wasting more time. Here we go. And that last region, is everything that's outside of your two circles. Okay? So, what I've highlighted here is how you link from a Venn diagram to the regions in a two-way table. Okay, so that's exercise 9E. As you're solving these questions, you'll be using either addition rule, two-way table, or Venn diagram, or a tree diagram to solve your problems. Okay? If you're not strong with your Venn diagrams and Carnot maps, you'll find 9F very difficult. So my tip is, if you're doing this exercise, please do 9E first. Otherwise, if you're feeling pretty confident from year 10, then start off at 9F. Okay, but this is what I would require you to do, or to at least understand. So what you see on the screen right now, that is your prerequisite before you do 9F. Okay? Assuming that this is somewhat okay, these notes are all on OneNote. You can copy the notes down, but that's what I need you to know. Okay? Let's move on to 9F. So today's lesson, I want to talk about the concept of conditional probability. Okay? And as I'm describing it, I will use tree diagrams. I will use Carnot maps, or the at least multiplication rule with the Carnot maps to help you understand what it is. Okay? And Venn diagrams. Here we go. Let's do this. Conditional probability. They give you this rule, so most students will copy this rule down and they will just know this as conditional, but I need you to understand what this means. Okay? So you've got probability of A given B is equal to the probability of A intersection B over probability of B. Okay, this is the rule. This is actually simply from your multiplication rule. Okay, I'm going to draw a tree diagram so you can understand how this logic happens. Here we go. Tree diagram. Say you got two options, event A and not A. Okay, so you either get A on the first go or you don't get A on the first go. That's the idea, right? So if I roll a dice, you either get a 3 or you don't get a 3. Okay? Then you roll the dice again. Now, when you roll the dice again, this is a second event. Okay? So I'm going to write down here, let A be getting a 3 when rolling a dice. Now, let's just go with our own general probability. What's the chances of getting a 3 on the first go when you're rolling a dice? What's the chance of getting a 3? Roll a dice. 1 in 6. Chance of not getting a 3 then? 5 and 6. Very good. Now, usually, and there's an assumption here, usually we already know that rolling a dice, it is independent of what happens prior. So if I said, what's the chance of you now rolling again and you get a 3? Okay, so this is where some students will get confused. They're like, but does it matter whether you had the 3 in the first time? Or doesn't it? It doesn't when we're talking about independence. When we're rolling a dice, we would then say the chances are still the same. Every time you roll a dice, you still have 1 in 6 chance of getting a 3, right? This is not conditional. See, what is conditional probability? That second event does depend on what you get the first time. The way that I like to describe it is if I walk to school every day and I take the same path, so it's the same path that I walk. If on Monday I walk and there was a twig and I tripped over on Monday, right? So say I trip. Let's say the chance of me tripping is 90% because I'm very clumsy. And 90% I would trip on the Monday. Now, logically, on Tuesday, when I'm walking again on the same path, am I more likely or less likely or the same chance to trip over that same twig? Logically. Most likely. Now, regardless whether it's most likely or less likely, the problem is that Monday had set an influence on my next day. That's called condition. Because if I trip over Tuesday, I'm like, oh, damn, it's the same twig. Then Wednesday, am I more likely to trip again or less likely this time? Less likely because apparently I've learned. Yeah? Apparently. Wednesday, if I see the twig again, I may trip again if I do, 3rd time in a row. Then Thursday now, you would say, no, surely after 3 days in a row, he should have learned his mistake and not trip again. So what's happening here is that each time I go, each event, there is some influence to the next event. So it does matter whether I did trip on Monday. It does matter if I trip on Tuesday. It does matter if I trip on Wednesday, because each time it now has a significant increase or significant decrease in my next event. But independent events means that every day I'm going to walk by this path and that twig, if every day, Monday, Tuesday, Wednesday, Thursday, Friday, I'm still going to trip over that twig, that means I don't learn from my mistake. That means every day I have an equal chance of tripping over that twig. Sorry?
What kind of stick are we talking about?
I don't know. I'm just trying to give you the idea. So the idea is that conditional probability means that whatever happened before does influence what happens later. You think of it as like if it rained today, the chances of it raining tomorrow could be higher, it could be lower. It could be higher because we're in the raining season. It could be lower because it's already rained, so tomorrow might be better, right? So regardless, the fact that it rained before has an effect on the next day's raining or not raining, right? But things like flipping a coin, rolling a dice, it doesn't matter if you had a 3 beforehand. The chances of you getting a 3 again is still independent of that. Is that you keep flipping, and it doesn't matter how many 3s you had before. It doesn't matter how many tails you had before when you flipped the coin. It doesn't matter. It just means that every time you flip it, you still have the same chances of getting it. This is one of the flaws when it comes to gambling. When people come in and they say, oh, it's been 7 7s in a row, that means the next one can't be a 7. Like, no, you can't say that because every time it is the same chances of it coming. It just happens to be 7 7 7 7 7, but it doesn't mean that now it's more likely to be. When you're thinking more likely, what you're doing there is you're following what we call conditional probability. We think that whatever happened before has an effect on what happens later. Some cases it's true, and some other cases it's not. Your goal is to learn the difference between the two. The reason why you need to know the difference is when the questions in year 12, they will give you a scenario whether it is dependent, which they call conditional, or a scenario that is independent. And it's only different by one mathematical concept, okay? So this is how it works. So normally, say if I change the scenario and say this was about me tripping over a twig, right? So I'm going to change the scenario. Say A was the chances of tripping over a twig, right? Say I had 90% chance. That means I had 10% chance of not tripping. If I then say that the next day, so this is Tuesday, chances of Tuesday for me to trip again, and I then change this to now 0.7 because now I'm more aware, okay? What we then call this branch, and this is where it's key, this branch is the probability of B, so we call this branch the chances of B, so probability of Tuesday, So say if A was Monday, I'm going to write here Monday. So if A was Monday, then B is now Tuesday. This is chances of B given. So providing that I had already tripped the day before. That's what that's trying to say. So when they say, when you write probability of B given A, what you're looking for is just this, just that branch. Okay? Then, what you've learnt so far from year 7 to year 10 is you've learnt how to find this entire branch. This entire branch, we call that chances of you tripping on Monday and Tuesday. That's what you've learnt. So back in year 10, how you would have worked out the probability, which is what we call the multiplication rule, you would have said chances of you tripping on Monday and tripping on Tuesday, so both days, what's the chance of you tripping on both days? Well, you would have done 0.9 times 0.7. And what you're doing here, you're actually writing down the chances of probability of A times probability of B given A. Can you see what I'm doing there? This is where your multiplication rule came from. Can you see where that idea comes from? Because that's what that is. When you're doing your multiplication rule, you're simply saying, this is the first event. This second event does depend on the previous event. Okay, and if it does, then together, the chances of both of them occurring at the same time, and that's what you were learning in 7, 8, you're learning what the word and or is for union, and is for intersection, right? So here, we're saying the chances of Monday and Tuesday tripping over was equal to 0.9 times 0.7. What you were doing is you had a 90% chance on day 1, and then on day 2, it's 70% of that 90%. That's why you're timesing it, not adding, not subtracting, because you're saying it's 70% of the 90% chance over 2 days. That's why you're doing 0.7 times 0.9. That gives you the chances of the 2 days of you tripping, okay? And so that overall, then they said that's the rule. They called that the multiplication rule, but essentially you're just following the tree diagram, but not knowing that that second event was dependent on A, okay? So this multiplication rule, all they did was they rejigged it, okay? If you wanted to get this section, just that branch only, so just this section here, B given A, that 0.7, you just divide both sides by probability of A. So here, if I rewrite this, if I said divide both sides, divide this side by probability of A, divide this side by probability of A, you can see probability A divided by probability A cancels out, and you get probability of B given A is equal to probability of A intersection B over probability of A. And this is what I was describing here. Okay, so if you look at their similarities, both rules are the same. Chances of A given B, well, it depends on, it's divided by B. Here, chances of B given A, it's out of A. Now, for those who understand that mathematically through tree diagram, great. If that still doesn't get you, then I've got another example visually. Now I'm going to use a Venn diagram to describe what conditional probability is. Okay, so here's an example. Let's take, was it this example? Or was it this one? Yeah, I'm going to do this one, 18. So have a look at 18. I'm going to get you to think logically this time. So I tried to explain it through a tree diagram, and we talked about tripping. Say I give you this one now. So example 18. Suppose we roll a fair die and define the event A as rolling a 6. Okay, so A is getting a 6. Event B is rolling an even number. Okay, what is the probability of rolling a 6 given the information that an even number was rolled? So what are they trying to say? Let's draw a Venn diagram so you can picture this. Rolling a dice. In this box, this is your universal set. When you're rolling a dice, what are the total number of outcomes that you can get? 6. Yeah, we're going to say a normal 6-sided die. Because they said fair die. Fair die normally means it's 1 to 6. Okay, so you got 1, 2, 3, 4, 5, and 6, right? These are your elements. But they told you specifically that A is getting a 6. This is 6. So I'm going to put, that's my A, right? But they then said B, the event B is getting an even number. Okay, so which ones are my even numbers? 2, 4, and 6. So if I rearrange this now, I'm going to rearrange it so that it looks more concise. So 2 and 3 is out here. This means this is B. True? That's B, and this is A. So what you can see is A is a subset of B. But what's interesting here is you're now asking, and we can do it logically, you don't even need to use a formula here. If I asked you, what is the chances, the probability of getting a 6 if you already knew, say, the information that you got an even number? What does that mean? It means that out of your 6 numbers, you know you got one of these 3. 2, 4, or 6. That's what they're trying to say. Given that you already knew you got an even number, what's the chance of getting a 6? What would you say? 1 and 3. Because there's only 3 options left, and that's because you knew it was B already. They already told you. You got B. You got B. It's 2, 4, or 6. Now I'm asking you, what's the chance of getting a 6? Then logically you would say, well, chance of getting 6, there's only one of them, and it's out of 3. But what have you really done here is you found the probability of getting a 6 intersection even. Because I want to get a 6 and I want it to be even. So what you're really doing here is A intersection B divided by, out of your lot, what was the sample that you were getting from? You got it from probability of B, or the number of B's. So the B's, you had 2, 4, and 6. So essentially, can you see it's just A intersection B. What's the intersection between group A and B? There's only one, which is the 6. And then this is B. That's where the rule's coming from. So if you think about it, I'm just saying what's the probability of getting, sorry, I should write that again as probability of A, so chances of getting a 6, given that you knew you got a even number, you're essentially just doing a conditional probability that looks like this. You're saying, if I already knew I got a B, the sample has to be out of B, which is even numbers. So out of a list of even numbers, 2, 4, and 6, what's the chance of getting a 6? But the 6 is, well, where do they both collide with each other? I want a 6 and it needs to be even. That's there. That's why you said it's 1 out of 3. So this is a visual aspect of conditional probability. This one is the tree diagram to describe what you were learning from 7 to 10 and understanding why you did 0.9 times 0.7. Because what you're really doing is this second chance is doing 70% of what? It's 70% chance of your 90% chance of tripping. Okay, so you had 90% chance of tripping the first time. Then the second day, it's 70% of that 90% gives you your total percentage of chances to trip, right? So that's what you were doing. You're doing probability of B given A times probability of A. That's how this came about, okay? And from that logic, that's where conditional probability rule comes out. If that didn't make sense, then this also makes sense too on what you were doing. You're essentially saying if B had already, the sample changes, instead of 1 out of 6, it's now 1 out of 3. Okay, so it's just getting your head around conditional, because if you get what I'm saying there already, G is very easy. G is one mathematical concept away from what you need to do. Okay, Jacob? Okay. How do we feel about this so far? Kind of on the edge. We'll do some examples together, but just your last notes for now. This is your last note. So 9G depends on you understanding this one key concept here. So I'm going to write it again. This one right here. Probability of A intersection B is equal to probability of A times probability of B given A. I'm going to draw the tree diagram so you can follow me. So here we go. For a conditional probability, remember, event A is you either get it or you don't. Event B apparently depends on this happening or not. So here we go. I'm going to do B dash again. What you did was A times B is this is what you were doing. So we wrote down 0.9, 0.7, then chances of you getting A and B should equal to 0.9 times 0.7, right? Now 9G, exercise 9G, one small mathematical concept. So I want you to write this down. Exercise 9G, when they say independent events, and in the year 12 questions, if they say independent events, they're just telling you one thing. This is the one thing they're saying. PR of, sorry, I should probably just do this. A given B is equal to, or if we're going to use our tree diagram, I'm going to rewrite that. Probability of B given A, probability of B. Now I want you to have a think about what I've changed here. Okay, if I said probability of B given A is the same as probability of B, what am I saying? Have a think about the tree diagram. What am I really trying to say? If I say that the given probability is the same thing as just finding the probability of B.
A is independent from B.
And what does that mean? So logically, I'm going to draw the tree diagram again. So what I'm trying to say here is that when I get A, this is your probability of B given A. But if I said the probability of B given A, this branch here, which I'm going to highlight again. Very good. Very good. And so what that means in independent events, it just means that means whatever you do at A doesn't matter. It will always going to be, probability of B is still going to be what it was meant to be. So you can keep repeating it. And that's the same synonymous to what I was saying before, that if every day I walk, I have 90% chance of tripping, it doesn't change. Whether it's Friday or next Friday, I'm still going to have 90% chance of tripping. So it's based on this one small key change that when you're finding probability of A intersection B for independent events, this is key because when you're doing exams next year, when they say it's independent events, the only difference is that. If you're trying to find A and B, the only difference is that B and A are not related to each other anymore. So you can multiply these two together and that will be your independent, that's your intersection. Okay, so that is 9G. So 9G is very easy. 9G just wants you to practice recognizing when they say independent events that you use this rule. When they don't tell you it's independent events, you are using this. And you've been doing that since year 7 to 10. Okay, we just don't call it conditional. You just didn't learn that this branch right there, the second branch there, is a conditional probability. You're now learning that as the name. And I'm trying to get you to understand the questions they're going to put in. Now, the textbooks is not as good because they often use the word given. You'll find that in that text, that exam that for this year, they use the word given. Normally in the past exams, they don't use the word given. You're meant to understand the scenario that something has already occurred. What is the chances of getting that? You're meant to know that that's conditional. Okay, so the key word that you're doing in your exercise books, they'll use the word given, but don't rely that it's always going to be the word given. You have to understand the scenario. And the difference between independent and conditional is really just on that idea. Is something happening that depends on something before, or is it independent of each other? That's all you need to know. Often it depends, they'll tell you. Conditional probability, you have to think about it. You have to think, is this occurring? Is it affecting another event? If it is, that's conditional. Okay? All right, I'm going to stop here and I'm going to go around. I want you to work on exercise 9E if you're not really strong with Venn diagrams and cardinal maps or two-way tables. But 9F is what I want you to work on. Okay, so this year, if we were to conclude, even if you're not able to do 10C, 10D, okay, 10C's combinations, I want you to learn 9F. Okay, 9F is big. What Dylan's got over there, that exam, question 4 was conditional probability. Okay, so that's all related to 9F. You have to know it. Kids suck at it and they hate it. Yeah.
It's a binomial distribution.
It's a binomial distribution.
Just tricky. You didn't have to think about the formula for conditional probability.
No, but you need to understand it though. Yeah. So that's what I meant. That you don't use the rule, but you need to understand the concept though. So 9F is what I think is most important. That's what I would want. If you're doing methods next year, this is the part of the concept I haven't taught. And I haven't taught anti-derivatives, which is unfortunate. I would have preferred to